Now, so ladies and gents, today we're going to carry on from where we finished off last week. We were looking at the theorem of superposition. So we're going to recap that by going through a circuit that's got a current source in it as well, because we talked about current sources last week but never really went through an example with a current source in it. And then we're going to look at a slightly different theorem for circuit analysis, and one that is particularly useful where you want to see how a network's going to perform over a range of different loads, because it simplifies the circuit so that you can then do easy calculations to what's going to happen with regards to a different load. Okay? So it's one of the most handy techniques in electrical analysis, really. Sometimes you get a situation where you can use more than one technique for an overall. And what we'll look at the circuit we did last week. Towards the end of this session, we'll look at how you can analyse that using Thevenins theorem as well. Okay, so up front, we're going to see if we can solve this circuit using the theorem of superposition, like we did last week. Okay, so what we're going to analyse is find we'll call that I3, I1, I'll call it I2, sorry, and we'll call this one I3, and we'll call that IS, because that's the source current.
Put two I3s.
Have I put two I3s? Oh, sorry. We'll call that I1 then. Well spotted, Luke. Okay, so we're going to analyse that circuit using the theorem of superposition, like we did last week. Let's join those together and make it a little smaller so I've got a bit more room on the board. So, what's the first step in the process to use superposition? Well, what overall have we got to do? Anyone like to have a go at telling us that?
Do you find the total resistance?
Not at this stage, no. Perhaps someone who was here last week. What does superposition say? How can we find... We've got two sources, so we've got current being delivered from this current source of 8 amps over here, and we've also got current being delivered.
Removable. I'm going to replace them.
Yeah, so overall we analyse one source, analyse the other source individually, and add their contributions together to get the overall.
Last week we just had two voltage sources, didn't we?
Yeah, but this week we've got a current source and a voltage source. Okay, so what we do is we first of all consider the circuit. So what we'll do first is consider the circuit with just the current source. What have we got to do with the voltage source, the battery, to be able to do that?
Take it out.
Take it out, yeah,
Okay.
and short circuit it. Okay, so what I'm going to do is just put a line through it and a short circuit across there for this version of the circuit. We replace any source with its ideal internal resistance, and as you learnt last week, the ideal internal resistance of a voltage source is 0 ohms, and therefore we replace that source with a short circuit. And then we analyse like we would any other normal circuit with one source in it. So the only thing we know at the moment is that we've got 8 amps flowing as IS, and we got the values of the resistors. Okay, and in that circuit, where would we assume, what would we assume the direction of this current up here?
Going down through that resistor.
It would go that way. And we'd, using what we did last week, we'll call this circuit A, and so we've got ISA, I1A, I3A and I2A. Yeah. What can we do now to, in an effort to start solving that circuit?
Total resistance.
Yep, find RT. So how are we going to do that?
Well, you take out the other source, aren't they? Just 3 parallel resistors.
3 parallel resistors, yeah. So RT is equal to 50 to the minus 1 plus 30 to the minus 1 plus 2 to the minus 1. What's the estimate of the total resistance here? What do we know it's absolutely going to be? No?
Well, it's going to be more than 2. It's going to be less than 50.
Is it going to be more than 2? If there's 3 different ways for the current to go, Carl, overall the resistance is less than the smallest one. Always in a parallel circuit, the total is always going to be, so it's going to be somewhere less than 2. So push the buttons on that, please. I get 1.81 ohms. Anyone disagree with that? Pause video now. So just to sum that process up then, for those watching the video, we short out the voltage source with its internal resistance of 0 ohms. We're analysing to find the 3 currents ISA, I1A, I3A and I2A. First thing to do is find the total resistance, so we've done that there, 1.81 ohms. Then used all the 3 resistances in the circuit are in parallel, so that means all the 3 voltages across the resistors are the same voltage, and we found that 14.5 volts there, and then we used that 14.5 volts 3 times with the 3 individual resistances to find I1A as 0.29 amps, I2A 7.25 amps and I3A 0.483 amps. So we've got the currents in each leg for circuit A with the current source. The next part of the process is that we need to analyse the circuit for the voltage source. So what we're talking about doing here is analysing this circuit B ES only, the voltage source only. So, what do we need to do?
Take away the current source.
Take away the current source. What do we replace it with?
Short circuit.
A what?
Short circuit.
What's the ideal internal resistance of a current source?
Infinite.
Infinite. So we take it out and we leave it open. Yeah? Open circuit. So effectively what we need to do is completely remove the current source from the circuit. Like so, and leave it open circuit. So if we were now to put current arrows on there, which way would I put current in this leg where the battery is?
Up.
Up or that way. So that's I2B. And then in these legs,
Down for the resistance.
both down. Yeah. I3B
We're technically put it in the circuit.
and I
In real world. Circuits.
1B.
There's not open circuit there. It's just like through here.
How much IS current flows this time? How much current through the current source? None. Yeah. No current down there. Yeah. Which makes sense. With open circuit, that is not contributing to circuit anymore. Okay. So, what is the process starting to determine?
Current.
Finding the currents in the yeah. So we want to find. Going to focus on finding the total current. That's going to be this one, because it's everything that comes from that battery has got to go back to up here somewhere. Yeah. So how are we going to do that?
Start with
Control over 2.
Find what? What are we going to find first?
Oh yeah. Total resistance.
RT. Yeah.
2.
So we'll find RT. That will. What will be else we'll be able to find once we've found RT?
Total current.
That'll give us the total current. Yeah. We'll then find I2B. Then what we can find next, after we know I2B,
Work out the other one to take it away from the total. If you know the total and then one of them, then
yeah, so how are we going to find the second current? Either I1B or I3B?
you take it away from the total.
Yeah, but how are you going to find them? Yes, you've got to find the voltages. So which voltage can you find once you know I2B?
the first one.
You can then find VR2, yeah, which will allow you to find VR1 and VR3, won't it? Because you'll be able to take it off the total. Okay, so you'll be able to find VR1 and VR2 for it, VR2 and VR1 for instance, and then you'll be able to solve the circuit by finding the two currents, the two remaining currents. So that's the process. I'll pause the video there. So just to summarise that process for the video, went through and found the total resistance, 20.8 ohms, used that to find I2B, 578 milliamps. Having found that, it allowed us to find the volt drop across V2, 1.16 volts. Then taken that away from the source voltage using Kirchhoff's voltage law, we got the volt drop across VR2 as 10.8 volts, and then used that voltage to find the current I1B. We could have used Ohm's law again with VR3 and R3, but I've used Kirchhoff's current law here, taken I1B away from I2B to end up with 0.362 amps. So what we need to do now is pop back to the original circuit and add on these currents. So I'm just going to pause the video again now. Right, so what we need to do now is put all these currents back on this board. I'm going to put the ones due to IS in blue and the ones due to ES in green. So we know we got 8 amps flowing there. What was the current I1A? How much was it?
0.29 amps.
0.29 amps. I3A was down. And what was that?
0.48 amps.
And I2A was
7.25 amps.
yeah. And then in green we had no current through the source. How's that way? In what way was the current in this leg? What direction? Would have been down, wouldn't it? Yeah. And in this leg, down. But in this leg, up. Yeah. So, and what was I1B? 0.216 amps. I3B
0.362.
and I3B.
Oh, sorry, I don't know what I'm thinking.
Oh, sorry, I2B. That's I3B.
Yeah.
This is I2B. Sorry.
578 milliamps, was it?
0.578 amps. Yeah. And then we consolidate each of these by looking at each of them in turn. If the current arrows are in the same direction, we add them together to get the overall current. And if they are opposing each other, we take the smallest one away from the biggest one to get the overall, and the direction will be in the direction of the biggest current. So the overall currents in here is going to be that way, I2, that way, I3, and that way, I1. I1, I3, and I2. And we find them by saying that I1 is equal to I1A plus I1B. That is 0.29 plus 0.216 equals I3 is I3A plus I3B, which is 0.48 plus 0.316, 362, sorry, equals, and I2 is I2A minus I3B, because they're in opposite directions, which is 7.25 minus the 0.578 equals. So if we push the buttons on them, got some results for us. Top one, I1A, 4506 amps. Next one, this is
0.84.
0.84 amps, and this one 6 point something.
6.67.
Yeah. So long-winded in a way, but as long as you remember that process and what you have to do, each step, replacing each source one at a time, use separate diagrams. And one way I'd do it, if that was just in a notebook, would be to split the page in half and put one diagram for the diagram for circuit A and circuit B either side of that line, and do the calculations side by side, and then add them all up at the bottom to get the final result. If you run out of space, you could do that. You could do the total, what we've done here, on the opposite page, so you could put the two calculations on opposite pages. Alright? So that's the theorem of superposition, where you analyse what it does for each source separately and add those effects together. Yeah? And if you're interested in voltages, you'd find the voltages across each component separately and then add them together as well, taking their directions into account. Okay? Are you all happy for me to move on to the next topic? Yeah? The next part is Thevenins theorem. Okay? I've got Thevenins theorem in words, a bit wordy, and it will become a lot clearer when we actually do an example. Any active network having two terminals A and B can be replaced by a constant voltage source, a voltage and internal resistance. The value of the voltage source, that should read Vs, is equal to the open circuit potential difference between the terminals A and B, and the value of its resistance of the network measured between A and B with the load disconnected and all sources of voltage or current replaced by that ideal internal resistance. Okay, so very wordy that is, but there's a procedure to adopt, and if you follow it carefully you can't go wrong. First thing you do is you remove the load resistor, that the one that you're interested in analysing. So this is a technique where we want to analyse for one particular component in the circuit, the load resistor, if you like. Okay, we remove the required load resistor, for which you need to analyse the current from the network, and it leaves two open terminals, A and B. We'll generally label those. We then use other techniques, and that might involve superposition or just normal Ohm's law or series, parallel resistance, etc. But whatever techniques we need to find what the open circuit terminal voltage is between the terminals A and B with the load resistor removed. Then we take out each source of voltage or current and replace all of them with their ideal internal resistances. So that is a short circuit for a voltage source, open circuit for a current source. We then calculate the resistance, the total resistance of that circuit, looking in from the terminals A and B, which is different to what you normally calculate. You normally calculate from the source end. We're looking at what is the resistance looking back in at the output. Okay? Determine that resistance. You then use the equivalent circuit to find the current through the load resistors. So what you do then is you've got one voltage source, one resistor, and two terminals A and B. I didn't mean to do that. That you So what this process effectively does would turn, and we're going to do it in a minute, that circuit into a circuit like this with one resistance R Thevenins, Thevenins voltage, a Thevenins resistance, two terminals A and B, and then we connect our load resistor on there, and the Thevenins circuit we calculated. This bit, if we do it for the 30 ohm resistor, let's say we're going to make that A and B, that part inside that red circle will act exactly like that part would for the whole circuit, as far as doing analysis was concerned. So what we can then do is we can analyse what would happen if we changed this 30 ohm resistor for a 20 ohm one, for an 80 ohm one, for a 100 ohm one. We can do it in that circuit, and as a simple series circuit to find the current, as opposed to lots of analysis on this circuit. Yeah, so we do the detailed analysis once, simplify the circuit into one source and one resistor, and then we can plug all our different loads on and analyse what happens with each load. Okay? So, we're going to use Thevenins now to calculate the current flowing and the power dissipated in the 30 ohm resistor in that circuit. Yeah? So the first part of the process is to make this our terminals A and B, remove that resistor and calculate the open terminal voltage. Okay, so we'll do that now, and then I'll summarise that on the video afterwards. So pause the video now, sum up results of that analysis. So what we've looked at here is we've found with the open circuit terminals here. Fed up with this board. Open circuit terminals over here. We've calculated the total resistance with the circuit open at the terminals A and B, 25 ohms. So that's the two resistors R1 and R2 in series. Use that to calculate the current flowing with the load resistor removed, and then we've got a loop here that says if we find the volt drop across R2, we'll also have the open circuit voltage because there's no current flowing in R1. So we've said that the Thevenins voltage or open circuit voltage is equal to VR2, which is the current times the resistance, 19.2 volts. So, having done that, the next part of Just going to put another slide in. So what we've got so far is we've got V Thevenins is equal to, and what value did we get? 19.2 volts. So we got that bit. The other thing we've got to do is find this R Thevenins. Yep. And then once we've done that, we'll reconnect our ohm resistor, and we'll be able to analyse what the current is in it. So the next bit is replace all sources with their ideal internal resistance. So I've taken out the voltage source and replaced it with its internal ideal resistance, short circuit. The resistance of an ideal current source is 0 ohms. What we're now going to do is calculate the voltage source. Yeah, so that was a voltage source, wasn't it? Ideal. Did I say current? I'm sorry. You're good at picking up my deliberate mistakes, Luke, aren't you? Yeah. So we're looking in this end. If we put what we're saying is, what would we measure if we put an ohm meter on those two terminals? So, what kind of circuit have we got for current there? If we're looking in that way, we're pretending that we're going to put a battery in here. What is the total resistance to that battery? R Thevenins is equal to, what would the formula look like?
5.
And that should be, well, I've got two R1s in this circuit, but never mind. We'll call that R4. Yeah. So what's the formula to find the total resistance, or the Thevenins resistance, looking back in this case? It's going to be R4 plus, how are those two connected, Carl?
Parallel.
They're parallel, so it's going to be R1 times R2 over R1 plus R2. So we got 5 plus 5 times 20 over 25. 9 ohms. That's 100, and that's 4. 100 over 4 is 25. Sorry, 29 ohms. Am I right? Oh yeah. 9 ohms. So the Thevenins resistance, 9 ohms. It's just that resistance looking back in at the terminals where you've removed your load resistor. So now we can add that value to our circuit there, and that will allow us easily to find IL, won't it? Because that's now just a simple series circuit. We, at this level, we can do that. We're good enough to do that all in one go. We can say IL is equal to V Thevenins over R little t, the Thevenins resistance, plus the load resistance. That's 19.2 over 9 plus 30 equals 0.492. And the power is I squared RL 0.492 squared times 30 equals 7.27 watts. Okay, happy with that? And we could equally then use that Thevenin circuit to analyse 20 ohm resistor, a 5 ohm resistor as a load, and so on, and it would act just like the whole circuit. Pause the video. Right, just want to look. What we're going to do is have a look at how we can use Thevenins on a circuit where there's two sources. So this is circuit, if not exactly the same. I think that is the one we analysed last week using superposition. So we're going to use Thevenins this time to find the current I3 and the power dissipated in a 30 ohm resistor. Yeah. So first thing we got to do for Thevenins is remove the resistor of interest and create two terminals I and B. Yeah? And then we've got to try and find what the volt drop is across those two terminals. Yeah? What would be your suggested way of doing that?
Removing one of the sources.
Yeah, so overall, Carl, what technique are you going to use?
Superposition. Is that it?
Yeah, if you're going to remove one source, what you're saying is you're going to go through the process of superposition to find
Total resistance.
well, you're going to initially you're going to use it to find this VOC voltage in the middle here, aren't you? Yeah, because if what you're saying is take that source out, so you must be going into a superposition situation, finding separately what VOC is for circuit A, and then do it for circuit B, and then add the two contributions together. Don't have to just be current that you use superposition for, you can use it for voltage. Yeah, so just going to make copy of that page. In fact, I'll do it twice. So, if we call this circuit A, and we remove V2, like so, and replace it with its ideal internal resistance. Yep. How would we draw a current on that board now? Let's just scrub that one out for a minute, because we've only got one current, haven't we? Yeah? Agreed? Yeah? So, we've got here a KVL loop involving VOC, A, and VR2, A. Yeah? Where VOCA must be equal to VR2A, because that's a clockwise loop and that's an anti-clockwise loop. Yeah? So we can find that voltage. How do we go about doing that? We need to find the volt drop across here, so what do we need to find? The current? Yeah? How can we do that? I is equal to V1. And what's the total resistance here? The current flow. How much current flowing down that middle leg? None. So all the current is going round the outside and through those two resistors in series. I know they're in a strange place. We've normally put them on the top. Confused you a bit last week, Carl, didn't it? Yeah?
Yeah.
But that is a series circuit all the way round the outside. So it's going to be R1 plus R2. That's the 12 volts over 11 ohms equals .09 amps. I make it. Yeah. Therefore, VOCA must be, we already said us equal to VR2A, and VR2A is equal to the current I times R2, which is 1.09 times 5 equals 5.45 volts. Yeah? Everyone happy with that? Yeah? Cool? Yeah. So now what we've got to do is do the same with that source. Short it out with its internal resistance when it's ideal, short circuit. Okay, and find now VOCB. This is circuit B.
We don't have another circuit.
You don't know.
Do it like this, look.
You're going to have to improvise, Lewis, because I didn't think I would think about doing it this way until now. So I do apologise.
Just put one on the page 4.
Scribble on it. Alright? I have done a lot of the work for you. So we're going to analyse. I'm going to leave you now to analyse that and find VOCB. Have we got this right in terms of that's going to be the direction of current flow according to that one if we're coming out of that battery? So we would have that voltage being that way, current flow is this way, that voltage is that way, so VOCB arrow is in the right direction. Just go back to the first one and make sure we got that one right. Current flow is that way, that is that, and that must be opposite, so we got them both in the same direction. So I'm going to pause the video, let you analyse that, and then we'll come back and summarise it. So pause video now. Start video now. Right. So the last thing we've got to find, haven't found our Thevenins voltage, is we've got to find our Thevenins resistance. So if I connected an ohm meter in there, what would I measure? What kind of circuit have I got? How are those two resistors connected? Forget about the current for a minute, let's cross them out. If I put an ohm meter in, think about this. How could I draw this circuit differently that would help me? I've got terminals A and B.
They're in parallel, aren't they?
They are well spotted, Luke. They're in parallel. If it helps you to draw the circuit out in a slightly different way, do it. These two resistors, I could easily take that one and connect it over here instead of over there. I'd have two resistors in parallel, or pull that one over there. They are in parallel. Do you all see that? Yeah? So our Thevenins is simply R1, R2 over R1 plus R2. 6 times 5 over 11. That's 30 over 11 equals Can't? Can it? What is it then? 30 divided by 11.
2.72.
2.72 ohms. Yeah? So we can now go to our Thevenins equivalent circuit. There it is. And put 2.72, what was that, Carl?
Yeah, or 2.727, so 2.73 actually.
2.73 ohms in there. Okay, and then it's quite simple then to calculate IL, because it is V Thevenins over R Thevenins plus RL. That's 10.9 divided by 2.73 plus 30 equals. We get those. Huh? Still drawing it.
Still drawing. Second.
So where did the 30 ohms come from?
That's the load resistor we took out in the first place, Tony. Yeah?
Yeah,
That's alright.
so long ago I forgot.
0.33 amps, and P is I squared RL. .33 watts. Now the $1 million question is, does that stack up with what we calculated using superposition last week?
It's a 3.3.
I 3.4 watts. Yeah, 0.341.
Yeah.
What? 3.4 watts.
Yeah. I'd suggest there's probably a little less rounding carried out in this process, because if you think about it, in a superposition you've calculated separate currents for each source that you've probably rounded a little bit. So you've done a lot more rounding in a superposition method than you have in this.
But then you
did superposition with this. But I think, you know, you're never going to carry all your results through. We've definitely got the same results as we got with both methods. Okay.
Although with this method you have to use the other method as well.
Yes. Because it's got two sources.
Yeah.
Or use some other technique to analyse the circuit with two sources in them. Alright?
Is that IP? Is that I2? Is that I2 squared?
That should be I squared, Tony. Well spotted, mate. Another deliberate mistake of mine. I squared
It should
R.
also be IL. IL squared.
Yeah.
So I think the other as well.
But there's only one current, isn't it? Yeah, you could.
Well, no, because you've got I1 and I2 from the superposition, so that could get mistaken.
You're quite right, you should be specific.
Sorry, can you just
Down again, Tony. Alright. Now, what I was wondering is, if I work it out and we got time, do you think that might help if we actually built a network similar to that first one with 4 or 5 resistors in, done analysis on it for a load resistor, we could actually find out what the open terminal circuit voltage is by taking a resistor out and measuring it. We could short out the source and put an ohm meter on and find the Thevenins resistance, and show that it would act the same when we connected up just the Thevenins voltage and a series resistance according to the Thevenins resistance, and connect the load resistor back in and see we got more or less, you know, a back experiment, more or less the same current. Would that help to sort of kind of understand where this is coming from, or at least prove?
Yeah.
We can either, if I think we ain't got quite enough time, we do it with multi-sim instead of real practical, but think about doing that after the holiday.
Yeah,
Yeah?
that's a good idea.
And that will help to recap what we've done before we go on a little bit further.
So
Yeah?
happy to remember as well.
Yeah.
Practical, yeah.
Alright?
Yeah.
Yeah? So, in your notes, in the meantime, in the notes I gave you last week, there's some example questions around the use of Thevenins theorem. So, you can spend the rest of the session having a go at one of them, or if you want to have a look at the assignment you've got handed in later today, then, and that's not finished,